All right, 6.5, we're still in, for those of you starting this video, where this is Calc 2, which is Math 66 here. We are doing 6.5, which is on surface areas of revolution. Area of revolution. And not like Viva la Revolution and take over the government, like revolve around something. You should call it rotation, because revolution is a touchy word sometimes nowadays. All right, so let's take a look at the picture. What we're doing is we got some function. This is our f of x. Y equals f of x. And from A to B, we're going to take this bad boy and revolve it around the x-axis, just like we did in the other chapters. This is going to make a nice little vase. A vase going sideways. It's going to look a little bit like that. So we're rotating it around the x-axis. Pretend this looks symmetrical. And it's got like, there's no ends, so I guess it's not really a vase. And what we're going to do is we're going to do a ring at a time. And since this is going around, like this is going around the thing that revolved, this ends up making very something like a cylindrical shell. It's very much a cylindrical shell, in fact. So like if I put my axis back in it, my R here is my height. But my height is changing. So like the left side of the curve has a different height than the right side. So we're not going to call it the height, we're going to call it the slant height. And so this ends up being, rather than like a dx or a dy, this ends up being a ds. The slant height is a ds. And so like our surface area, we got to account for the cylinder. So we're looking like at a dA, we've got 2 pi well, when we do ds, when we narrow it down to a infinitely thin thickness, it's still approximately just like f of x there. But we still have that ds, that slant is in there. So that's what we're going to have as our dA. This is like our radius. And this is the width of our ring. So that's a ds right there, the width. So the two common setups for this is when ds is along x, we're going in the dx direction, we'll have like the integral from a to b, 2 pi f of x, or y, since y is the same thing as f of x. And then we'll have like 1 plus, since we're doing a dx here. And we'll replace this with the x or its equation. So remembering it that way makes it a little easier to see that that's the height, or that's the radius. I know why I keep calling it height, Cause I'm fucking looking at it go up. It's really the radius. That's why I'm saying it wrong. The height is literally that way. Radius is that way. There we go. Now I can say that right. R equals height, which is f of x. And ds, our width, our h is our width, which is ds. Slant height. There we go. We're so used to doing stuff in dx, so we do the revolving around x-axis first. But then, like, if we have height in the formula, it sounds like. All right, our other option is we could do this from C to D, or if we're going along dy. So we'll have a 2 pi x, 1 plus dx dy squared dt, or d. And this is going to be slightly different than the last one. Because when we add in the x of t, y of t option here, we still want to have whatever this is, t1 to t2, 2 pi, whatever the radius is here. I'm just going to say radius. Might be y, might be x. But then we have our dx dt squared and dy dt squared dt. Because this is our ds there. It's the same ds as in the last section. In the first example we're going to do it both ways. Do it as a function of x and a function of y, and we'll see that we get the same value. Which means you'll be able to see that you have options. If one integral looks like shit, you can try the other one. That's nice. That's always nice when you have options on problem solving to find the same answer, do it a different way, that's easier. You haven't always gotten that. In fact, have you ever gotten that in like Calc 1? Have we ever had that? Not really. I don't recall it. You know, I scanned it. I'm messing with it. Some people are still writing. I got a fish. Anyone need longer? I can't tell with you. I think you're just sketching and editing. Are you good? Do you need this longer? Just clean it up. So our first thing, well, let me rewrite things that we needed. dA is 2 pi r ds. And s is like the integral from a to b, 2 pi y, some version of this, 1 plus dy dx squared dx. So our first example, we're going to do y equals x squared. We're going to do 1 is less than or equal to x, which is less than or equal to 2. And we'll rotate around y. So it's worth sketching. Especially since we're going to do this both ways. It's good to know the x and y values. So when x equals 1, y equals 1, when x is 2, y is 4, we're looking at that part of the parabola right there. And that's what's getting rotated around. So it'll look like a cup. Yeah. Effectively. So like the circles are going around this, so the radius is that way, which means the radius is in terms of x. Which is different than the one we had up above, but that just changes this. If we have x, we're using dx dy squared there. No, we're not. That's still dy dx. It's got to match the dx here. We're integrating along dx, and our radius is x. There we go. All right, so y is x squared, so dy dx is 2x. And our radius is x. Since we're doing, I'll put in the limits of integration afterwards. We have 1 plus 2x squared dx. And since this is along dx, we're doing x's from 1 to 2. And I'm just going to square that term there at the end. So we have 1 plus 4x squared in here. Any ideas? Anybody? Let's do a U sub. When we have something outside of a function and something inside the function, it's always a good thing to try doing a U sub on the inside. So we'll say u equals 1 plus 4x squared. So du equals 8x dx. And so like, if you want to look at it this way, 1 over 8x du equals dx. And I'm going to do new limits of integration here. When x equals 1, u equals 5. And when x equals 2, 2 squared is 4, times 4 is 16, plus 1 is 17. So we'll have 5 to 17. We had the 2 pi x, and we're changing it to du, so we're going to have 8x on the bottom. This is the square root of u now, du. So that looks like that cleans up to pi over 4 there. We have pi over 4, I'll pull the pi over 4 out. 5 to 17. I'm going to write the square root of u as u to the 1/2. And this becomes an easy integral. Up power, divide by the power. 2/3, and we still have the pi over 4 out front. We're going front, oop, that should say 17. Okay, 17. Should get pi over 6. 17 root 17 minus 5 root 5. I'll be honest, I'm happy with that answer. If you want to put a decimal after that, that's fine. But you should show the exact version. Any decimal you do is probably going to be approximation. I don't think square root of 17 is going to give you an ending decimal. All right, so let's take a look at doing this. Let's do it with dy. We still have 2 pi. This is the radius is still x, that hasn't changed. But now we're going to switch to 1 plus dx dy squared dy. Which means we got to switch this over to y's. It looks like y is going from 1 to 4 on our graph. The graph hasn't changed. The picture's still the same. And y equals x squared. We take the square root of both sides. We get x equals y to the 1/2 or square root of y. In fact, that's what I'll put in here for that x right there. Square root of y. So we're going to take the derivative. We need dx dy, right? We've got x. Dx dy, we bring the power down, we drop it by a power, which is like 1/2 square root y. That's my dx dy. If I square that, dx dy squared looks like 1/4y. That's our setup. This looks ugly, but it cleans out really, really well. Just going to have to do a little manipulation. I don't like having a couple square roots here, and we're going to address that. Since we're doing dy, I got to put my limits on there, 1 to 4. Since we figured them out. You guys with me? All right, so we got 1 to 4. I'm gonna put the pi out front. What happens if I move the 2 inside the radical? What does it look like inside the radical? It's like a 4, right? the square root of 4 would be 2, so if I put it back in, I could have like 4y in the radical. So what I'm looking at is like this. But when I have two radicals, I just put them together. This ends up being one radical of 4y times 1 plus 1 over 4y. And this was where you'll see it clean up pretty well. This just ends up being the square root of 4y plus 1 dy. So let's do a u sub. Say u equals 4y plus 1. So du is just 4 dy. Or 1/4 du is dy. When y equals 1, u equals 5. When y equals 4, u equals 17. Starting to see those numbers we had on the other one, right? And this becomes the integral of pi 5 to 17 u to the 1/2. And then we have 1/4 du. I'm going to put the 1/4 out here as pi over 4. Make that a pi over 4. 1/4 is coming out. And take a look at this. Ta-da! So we're going to see, we can fast forward to that since we've already done the work. Pi over 6, 17 root 17 minus 5 root 5. So the radius stays the same. It's got to be with the shape you made where you revolve it around. But you can choose to use it in the letter it already is, which made it easy up here, or you shift it to this. Sometimes it works both ways, so whichever one works best is usually the way to go. You guys ready for another? All right. On the next one, we'll set it up both ways. If we, well, we'll check the first way. If we don't like it, we can set it up the other way. X equals y to the 1/3. We're going to do 1 is less than or equal to y, less than or equal to 8. And rotate about x. So this correlates x equals y to the 1/3 is the same thing as x cubed equals y. And we know what the graph of x cubed looks like. I'm just going to fast forward there and say that's 8. That's that section right there. So it looks similar to the one we just had, just taller. But now we're rotating it about x. Which means this is coming down and this is coming down, and we're doing this. So our circle, it's like that. And our radius is in terms of y. So remember, we're doing 2 pi r ds. If we go with the r equals y, we're going from 1 to 8, 2 pi y, and we're going to want a dy. So this is going to be 1 plus dx dy squared. Well, let's figure out what dx dy is. Bring the power down, lower it by a power. And if we square it, we get 1/9 y to the negative 4/3. And this integral looks like shit. I don't know about you, but since we already know it works both ways, fuck all that. That don't look that friendly. I'll set it up the other way. The other way is gonna have, we need y as a function of x. So what are the x values on this range? X is going from 1 to 2 in that region. And we're going to 2 pi. We want y in terms of x for the radius. And y was x cubed. So that gives us an x cubed there. That's our radius. And now we're doing 1 plus dy dx squared here, dx. This is going to be a lot nicer because y was x cubed. We do y dx, we get 3x squared. So dy dx squared was 9x to the 4th. Pick your battles. If you've got different ways of solving it, do the one that works. I'm confident on your test, I'll give you a problem in one of these areas that says just do it both ways. Like one problem will be solved one way, another problem will be solved the other way. You'll know if you got them right if you got the same answer on both. There's a good chance you either got them both right or both wrong. But I like having that on the test. You can verify your answers with it. What is this looking like to you guys? It's like a U sub to me. I don't know about you. I'm gonna say U equals the inside. So du is 36x cubed dx. And so got 2 pi x cubed, putting the 36x cubed here. And then I've got the square root of u again. U. Now I need limits of integration. I've been switching to u each time. If you want to leave them in x, you need to make a note that you're leaving them in x. So you'll have to write x equals 1 and x equals 2. we've got pi over 18 there. U to the 1/2 du. Yeah. If I plug in 1, I get 1 per x, and if I plug in 8, the cube root of 8 is 2. Also, like sketching this graph, y equals x cubed. I know on 1 to 8, this is 1 to 2, but that's literally how you could do it. Plug in the limits in there. The limits. Good question. So we integrate. That goes up to 3/2. So we multiply by the reciprocals like that. Again, and we're going from x equals 1 to x equals 2. This is pi over, I think, 27. Let's see, 9 on bottom, pi over 27. I'm going to replace u back for what it was. 1 plus 9x to the 4th. This is 2 to the 3/2, which is like u root u. And now we're going from 1 to 2. If I stick in 2, 1 plus 9, 2 to the 4th. 2, 4, 8, 16. 16 times 9 is 144. Plus 1 is 145. So this is 145 to 3/2 minus. If I stick in 1, this is pretty easy. That's 10. So we have pi over 27 times 145 root 145 minus 10 root 10. I guess you could factor out a 5 if you wanted to. Pull out a 5. Let's see, 5 goes into that 29 times. But you don't need to. Do one more in class, and I think I'll do a short video doing one with parametric equations. The one I'd rather do in class is, let's find the surface area of a sphere. You guys need this up longer? All right. Let's prove the surface area of a sphere is 4 pi r squared. So, you know, good old sphere, we got a ball. One way we could do it is if we take a half sphere and like rotate it around x. Does that make sense? So like well, in 2D, a sphere is a circle, right? So let's start with the equation of a circle. X squared plus y squared equals r squared. That gives us a starting point to give us that'll give us our half sphere if we solve for y. So y squared equals r squared minus x squared. Which means y is the square root of r squared minus x squared. Have you guys done implicit differentiation? I can't remember if it's in Kaplan or not. I don't like taking the derivative of this. This one's pretty easy to take the derivative though. We're going to use implicit differentiation here. 2y dy equals negative 2x dx. So dy dx is negative 2x over 2y, negative x over y. And we already have y here. So dy dx is negative x over the square root of r squared minus x squared. It's a constant because the size of the sphere is, that's a good question. Since the circle isn't changing size, it's a constant, and derivative of a constant is 0. Now, if you take the derivative of this the good old-fashioned way, doing the chain rule, you will get the same thing. So if we square this, what do we get? So we saw that we use these squared a lot. This just ends up being positive x squared, and the radical goes away on the bottom. It's just r squared minus x squared. Does everyone remember implicit differentiation? Or it may not be great at it, but does it look familiar, the idea? You can get the same thing by taking the derivative here. Just rewrite this as y equals r squared minus x squared to the 1/2. And remember, r is a constant, so that when you take the derivative, it goes away on the chain rule part. So like if I revolve this around this, and if I want a dy dx makes me think I want to use a dx. So I want to integrate it this way from left to right. I'm going to do like this will be my ring. That way I can integrate from left to right. Which means my r here is y. That's handy because we solved for y. We got that in terms of y already. And we don't have a radius, so we're just using r to negative r, or negative r to r. Does that sound about right? So remember, our dA is 2 pi r ds. And we say r is y, so we're going to do 2 pi y. We already know this is negative r to r, no matter which way we integrate it, to be honest. And we're doing 1 plus dy dx squared. Just putting in the generic formula in dx. That's the generic version. Then we'll start replacing shit with what we got. Y is that fucked up square root. In here, we have 1 plus, we already did dy dx squared. So x squared over r squared minus x squared. Then we got a dx. Looks crazy, but if we put the two radicals together and multiply, it actually cleans up pretty nice. So I'm going to do that. I'll put my 2 pi out front. This is doing r squared minus x squared times that. So if I take this whole thing and multiply by that, I have r squared minus x squared. And if I take this whole thing and multiply by that, it cancels out and I just have plus x squared. And it looks like I didn't need to give all this extra dx. And this shit just got easy. The negative x squared and positive x squared go away. We have the square root of r squared dx. And that would be the absolute value of r, but a radius is guaranteed to be positive by its very nature. You cannot have a negative radius. So that's really like, if I wanted to, this is an extra step you probably wouldn't do. I could factor that out and just show that this is the integral of 1 dx. You don't even need the 1 in there. This just turns into 2 pi rx, evaluated from negative r to r. Pi r times r minus negative r. So 2 pi r times 2r. Bam. Wasn't that handy? You don't look impressed. You just derived the formula for the surface area of a sphere. You've used it before, but you didn't know where it came from, I'm sure. You just found it. You just got it yourself. Good job. All right, let's get the fuck out of here.
Just gotta hope that you don't end up deriving that one.
Yeah, probably not.
Hope you actually remember.
We'll do like an ellipse, ellipsoid.
You gotta remember that one. The amount of stuff I derived on it.
When you get to Calc 3 and you do spherical coordinates, I want you to know that I had a student get to the test, not remember the formulas, and rederive them on the test. When you see them, you're going to be like, what the fuck? If you remember what I said, that's what your response is going to be. Yeah, he didn't remember what they were, so he redid them. He was a high school student too. Motherfucker in a high school taking Calc 3. I don't think he was in his senior year. If he was, it was like the beginning of the senior year because he was almost had a mass or an AA in math by the time he graduated high school. There's only like 2 more classes after that one.
That's great.
Yeah, that impressed the shit out of me. I didn't even know he was a high school student at first.